Hi everyone. What I have here is a HP6114A precision power supply. I got it pretty cheap on eBay for less than $100, around 70 or so, and it seems to be working very well. Except it has some problems with the switches that control the voltage on the lower voltage scale, which are under 10 volts or so. So what I've done is I've taken apart the switch assembly, which I show over here. It's got this push button type decoder, which is fairly it's a self-contained unit, so it's hard to get into. But I removed it to make sure that these switches have the proper connections and contacts. But it's not going to be easy to get into it. As you can see, it's got these soldered into the board, and it's got these outputs that come out, which are decoded through this assembly, inside this assembly, and there's a mini PC board inside that actually does that. I'll show you the logic of the decoding a little bit later, but as you can see, you can switch through all the way from 10 millivolts on this unit, on this hundredths digits, plus a fine adjustment which goes to a 1 millivolt resolution. So this can go all the way up to, this particular unit goes to 39.999 volts, and it's very accurate above 10 volts, but I think the problems are in these two switch assemblies. It's noisy, and it doesn't sometimes register the change if I press a digit up and down. This, however, works very well, and I can see it actually. When I control it, it actually goes up by 1 millivolt and 2 millivolts and so on. So it's a very precise unit. The analog part of it is extremely good, and I will demonstrate that by connecting a decade resistance box, which is a very accurate box here. It goes up to 11K, and show this on this meter, which is also pretty accurate for the purpose of comparison or among different values, so it's consistent. Anyhow, let me turn it on and let's go through this quick demo here. It's now powered on, and right now I've set it at 5 volts. You can see it's right on, pretty much on target, very close to 5 volts. And if I reduce this voltage from 5 to 4 volts, you can see that it's now gone to 4, and I can control it in steps of 0.1 here. So this is 4.1, and if I go down to a lower value, let's say this is going to be 1 volt, you can see it's very much on target, and I can now step it through 10 millivolts. So that's 1.01. You could even go to 1 millivolt here, and that's 1 millivolt. So it's the internal electronics of this is excellent, and the internal reference, the currents, linearity, everything looks very, very good. So going back to 5 volts again, 5.001, and that's 5.001, very close. Of course, if I let it warm up a little bit, it's going to be even better. I go to 5 volts now. It's actually reading 5.009. So it requires some little bit of. The meter is probably not that accurate anyway, so I'm not going to go into that too much for accuracy purposes. But as you can see, it's very linear. If I go to, this is 3 volts. So it's working very well. So it's a matter of getting this contacts cleaned up. Hopefully, if I can do that, remove this board, remove this resistor out of this by desoldering all these, which is going to be the challenge. And I will basically demo, if I can, I'll see how far I can get with this one without damaging it. So here's the disassembled the thumb wheel switch, which I took off the board. I had to carefully desolder these pins off the board and then slide it out. In order to remove it, you may want to flex the portion of the board. Let me show you that. So here's the actual board, and you may have to basically flex this portion up and down to loosen the connections after you remove all the excess solder of these tabs. Then it should be able to slide out from here vertically out. So this is only the tricky portion in removing it, but now the more difficult thing is to get access to so there are 4 PCBs in here, and these are contacted by some kind of a ratcheting mechanism probably inside that selects 5 resistors which are in there, 4 or 5 resistors, and those are then decoded out based on the value shown on the top here. So this is probably the next step to see how far I can go with this. If this I can get cleaned up, then I think I have a very good instrument that will be matching the performance I just showed you with the Decade box. So after I took apart the 4 of these things, they are actually modular and they plug into each other. As you can see, there are these tabs which go into each other, so it's like you can just plug them into each other and you can make a larger array of these. So anyhow, the problem now really is to open this up without damaging it. I'm not sure if it's possible. I read online that once you open this, some of these springs can pop out inside and cause a problem. You'll not be able to put it back. It's looking at various ways of cleaning it or getting replacements if they are still available. So this is the real tricky part, is to somehow clean it. Whether I can spray something inside, I don't know. I'm just looking at options to see what to do with these. So here's the Durant 48611-468 switch. There are 4 of these in this unit, and there are inside each switch there are 5 internal contacts, A, B, C, D, E, and the black portion, the dotted black portion, shows you the actual switch. The resistors below are on the separate board which I showed earlier, and those resistors are chosen such that when you decode this table out, as the numbers are switched from 0 to 9, various switches come on and close. So as you can see, for 0 all the switches are closed, A, B, C, D, E. So you basically get a short from the extreme left to the extreme right terminal in that schematic. And as you go to 1, you'll get the B, C, D, E are closed, A is open, and based on how you choose your resistor values, you can get a linear progression from 0 to 9. So that's how the switch works. I've connected one of the switches. I put some wires on them, soldered some wires onto those tabs to make an exact measurement. The ones I have problems with are the 100th position switch and the 1/10th position switch in the instrument. So I'm going to see if I can measure those and see what they show as I go through the different digits from 0 through 9. In the 0 position, it should all be closed and should show 0 ohms or close to 0 ohms resistance. So here are the 4 switches now after I tested all of them. The rightmost 2 are the 1/10th and the 100th, which were giving problems. These 2 are okay, the 100th and the 10ths. I did spray a little bit of deoxide into that hole over there, as you can see right on the top side of the switch. And once I exercised the push buttons several times, these 2 switches, which were very in some positions were not working, are now fine. Basically, if you can get the 0 position to work, then all other positions should work, because 0 is the one that engages all of them, A, B, C, D, E. So once I cleaned that out, I think these 2 seem to be working now. They are making proper contact, and at 0 I'm reading about 0.18 ohms or so, which is a pretty good value, since external resistors are in the neighborhood of I believe in the hundreds of ohms or even thousands. So I think this should be good now, and once I put it back together, I'll do a measurement to see if it works. So the one I used deoxit D5 to basically spray down those little bit small holes, and I think that did the trick. I didn't have to disassemble any of this stuff. That would have been a real headache, putting it back together with the springs and stuff inside. So here's the moment of truth. I have connected the two leads from the inside of the instrument to the resistor controller here. Everything is soldered back in. Right now it's set at 0, 0, 0, 0. I'm going to turn it on. And it's now at 0, which is good. I'm going to switch the lowest 10th digit, 100th digits to 10 millivolts. And it's a bit noisy, but it's a bit high. It should be 10 millivolts. Let's try. Yeah, so this is the 100th 0.1 volt. It seems to be good. Earlier it was very flaky. 0.2 looks reasonable. So this is where I had seen the same problem earlier. As you can see, the switches are sensitive. So it's actually, once you touch the switch, it actually makes better contact. And then it's now 0.3, 0.4. I think some switches are still a little bit dirty. 0.5, 0.6. So let's try the lowest one again. 0.6 should be 0.61. That's correct. So it is now reading correctly. 0.61, 0.62, 0.63, 1.63, and 11.63. I think this is pretty reasonable if you can deal with some of the intermittent contacts. One has to make sure if you're applying it to any circuit that you test it before you use it, at least because of these switches are pretty old, and at this moment I don't think I'm going to be able to salvage them any more than this. So it is a bit touchy on this, especially on this 10th scale. So one has to be aware of that when you do this. However, if I keep it at 0, I think it might be okay. So yeah, 11 volts is right on target, 10.998. So overall, I think this is a pretty good result, considering I had totally random results earlier on when I switched in the 10th and 100th digits there. So everything is back together again. I powered it up, and setting is 11.11 volts, and as you can see, the meter is reading pretty close to that. 11.21, and it's 11.209, 1.21, and before this used to be really bad. Now it's actually reading pretty good, 1.2099. So I'm pretty thrilled with this repair, even though I couldn't fully get it to work. Especially this digit is a little bit flaky, but if I'm careful, I can make it work and get the right number out of this instrument if I just test it carefully before I engage it to any circuit. I mean, you've got to be careful, especially if this goes from this could be a 0.9 sometimes. So if you're not careful, instead of putting 4.9 or 4.1, you might put 4.9. 1.22, 21.22. Looks pretty good overall, especially on the higher ranges. I know it's very accurate. 31.22, and like this is the fine adjustment. So if I let this settle for a bit, 11.224. If I change this by 1 millivolt, 31.225, sorry, 30, then 31 point, sorry, this is 31.222, 31.223. So there's a bit of few millivolts of offset, but could be the meter, but it is moving by 1 millivolt, as you can see. So the fine adjust is just a rotary switch. It has no problems. It's very good, and this looks very nice. So you can have 1 millivolt or smaller resolution on this one, and the current control is done here. This one is not directly, doesn't read the actual value, but it's just a potentiometer which controls the amount of current. So you got to measure the current before you set it to some value. It's not doesn't read exactly what it shows over here. I think that's how it is designed. I'm not sure, because I was seeing totally different values on this. When I shorted it to a load, I would see a different current coming on, but I think this is very linear. Otherwise, it's just that it's there's no, the scaling is different from what you see on the meter here. So I believe these digits, yeah, one has to be careful. Other than that, I'm pretty happy. So as you can see, it just flakes out sometimes because of this contact here. So that's the end of this video. I hope it was educational to some extent. The main thing is this is a very well built instrument, and I think the only drawback or the flaw is probably in the switches, the way they implemented it, and it's likely to fail. If they had used rotary switches, I think it would have been a lot easier to clean them and do that, but I think they were trying to save some space, maybe use some decoding logic to get this done, but I just think it's a shame that the accuracy is ruined by these switches.